I think it was first noticed or at least written about in the early 80s. So, yeah. But it does seem to be universal for applications. We have a lot of temporary stuff we make and throw away, and it tends to dominate the applications we do. So it's a very effective observation about a lot of things. And the purpose of generation collector is to use that observation for efficiency. The way we use it for efficiency is if we know that we have this young generation, things that were recently allocated, and we know that most of this is dead because of the hypothesis itself, then if we applied an algorithm that is only linear to the line set, to something that is very sparse because of our assumption, we will get efficiency. That is the actual trick of generational collection. It's not the observation, it's the use of the empiric observation in combination with complexity tied to the observation. So if we use an algorithm that doesn't grow with the size of the heap space I'm collecting, but only with what's alive in it, and I know or hope that only 1% is alive, I will get a 100x efficiency boost compared to something that we need to scan everything. That's why we usually see copying collectors for the young generation and not a marked sweep compact collector, because a sweep is linear. Now, in order to keep the observation real, we can't just keep everything there. The observation is only that young stuff dies quickly, or that most stuff dies young. It's not that live stuff is young. In fact, the opposite is also true. Most live stuff is old. If it was young, it would be dead. So you have to evacuate, move away things that last long out of this space so that the observation would stay true. If you keep letting it stay there, then slowly it'll fill up and it will no longer be sparse, and your efficiency will go away. If your young gen fills up, it becomes less and less efficient by a factor of how much you can promote. So promotion is necessary to keep young generation going. It's impossible to keep an efficient young generation collector efficient if you don't promote long-lasting objects. So we only collect all generations when they fill up. We have this really cool filter in the young generation, and that filter is extremely effective. It's an order of magnitude or two in most environments, and it's so efficient that it's practically impossible to keep up with modern CPUs without a generational filter today. A modern x86 will happily allocate 1/4 to 1/2 gigabyte a second of new garbage. In fact, I like to say that its job is to generate garbage, and the side effect is the work you get. It is not the other way around. If I have a 32 vCore machine, it can happily generate 10 gigabytes a second of new junk. It's really hard to keep up with that without a generation filter. It's hard to keep even without it, without having a generational filter. It's virtually impossible. Okay, the way this works, by the way, is we keep something we call a remember set, and this is a remember set between generations, not to be confused with the G1 inter-region remember set. It's a different kind. And this tracks basically roots into the young generation from outside of it. Because we want to only focus on that sparse space, which means there are things that point into it from outside of where we're looking. We have to start from that as additional roots. An interesting effect, by the way, of young generation copy collectors, we don't need 2x the memory, and the reason we don't need that is because we can spill over to that big empty old gen if we need to. We have to start a young generation with enough room somewhere to put all the objects if they're alive, but it doesn't have to be in the young generation, which is why in some collectors, like all hotspot collectors, you'll see a survivor space that is generally much smaller than the Eden itself. It's not because you know it will fit, it's because if it doesn't fit, you throw it into the old gen, and there's room for that. Now, usually we want to keep the surviving objects in the young gen for a while, but not too long. I explained the why not too long, but for a while it's because if you just say anything that is alive now, promote, there'll be some things that were just allocated, maybe a lot of things, and they would have died if you just wait a little bit. So you lose a lot of efficiency if you don't let them stick around young for a little while before you promote them. It's not okay to say anything alive at this point, boom. You gotta age them a little bit. That in itself can have a huge efficiency effect if you don't do that. So a promotion threshold of 0 is not a good idea. Neither is an infinite promotion threshold. So you need to balance these out. Now, the way this remember set thing works is, well, it gets a little intricate, and I'm going to run quickly through this, but each store to a new gen, of a new gen reference, a reference to something in a new gen into somewhere else, an old gen, firm gen, will need to be tracked so we can know its potential route later. And most JVMs do this with what we call card marking or card tables. Every store to a location also potentially marks a thing saying, hey, there's something there that might point in the new gen. That is our remember set, those suspicious places we store outside of the new gen. And we use those in order to mark into to start the copy into the new gen. And right there is usually used to do this. Every store, every reference has a bearing on it. And there are lots of variations of exact technique there, and I won't get into those here. Typical combos of all this put together and collecting in commercial JVMs look like this. The young generation is usually, not always, but usually a copy collector. It's usually monolithic, and it's usually stop the world. The old generation is usually some variation of mark, sweep, compact, or mark, compact. And it could be any of the stop the world, concurrent, multi-concurrent, incremental variations amounted. Here are a whole bunch of other terms that I'm not going to spend the time to define. They're here for the slides for later. And here are some metrics. Metrics are important because things like allocation rate, how fast I make objects, well, as fast as you make objects, we have to collect them. Right? And the faster your application goes, generally the faster the objects will be made. It's almost a guaranteed linear relationship. Twice the TPS, twice the allocation rate. Another key metric is mutation rate. This is not how fast I make objects, but how fast I modify references in the heap. We, garbage collector people, call you the mutators. You're mutating the object graph we have to track. That's technically what we're talking about. So anything that can change references is a mutator, and how fast I change them as a rate is important. It's important if your algorithm needs to track it or deal with it or do something about mutations. And as you'll see, some of them do. Marking time and compaction time are metrics that, how big or how long it takes to do something. Especially if there's stop the world, you really care how long it is. I told you guys I'll show you how efficiency works here, so let's do that quickly. I said garbage collection is the best possible way, cheapest way to manage memory, right? And most people don't believe me when I say that, but let's go through an exercise. Imagine that I have an application that has a live set. Let's say the live set is a gigabyte. And I have a 1 gigabyte plus 1 word heap. Guaranteed all the time, use one empty word at all times. So when I allocate a word, I probably release the word. So when I allocate another word, the garbage collector needs to go find a word in a gigabyte. It's free, it's somewhere. It doesn't matter which of the algorithms we talked about we're pretty much going to use all the CPU for garbage collection. Every word we search a gigabyte. It's hard to kind of do that efficiently. However, that's an intuitive point, 100% CPU. The other intuitive point is that if I had an infinite heap, I would never have to garbage collect and not have to spend any time on garbage collection, right? And between those two, we have a very clean 1/x line that connects the two intuitive points. So if I had 2 words empty in a gigabyte, that's still pretty bad, but it's only half as bad as 1 word. If I had an empty gigabyte, I have to, every time I allocate a gigabyte, I have to scan a gigabyte. If I have an empty 100 gigabytes, every time I allocate 100 gigabytes, I just have to scan a gigabyte. If you apply an algorithm that is linear to the live set, the efficiency of garbage collection is completely under your control. All you need to do is give it a bunch of empty memory about the live set, and it will get more and more and more efficient. You're not happy with it spending 10% of the cycles on GC. You want that to be 5%, double the empty head. You want it to be 2.5%, double it again. Just keep going. And memory is cheap these days. This is just text that says the same. People who want to listen to this. And it's important to understand what empty memory actually does. It's an efficiency trade-off between CPU power and empty memory. And empty memory is often much cheaper than CPU these days. The amount of memory required and recovered basically will depend purely on the empty space, and the amount of work I have to do is fixed by my application. So the more empty I get, the less often I need to do the same amount of work. A copy or mark compact collector has this quality, a mark sweep compact does not, because of the complexity issues. Now, what do you control with this? Well, you control efficiency. And you control the frequency of pauses, because the more empty memory I have, the less often the pause will happen. However, you do not control the size of the pauses with this. Increasing empty memory spaces the pauses out. It doesn't make them smaller. In fact, in a lot of collectors, it makes them bigger. Anything that's linear to the size of the heap that you're making will grow when you improve it, but efficiency will improve. So if your goal is to reduce CPU spent on garbage collection, throw more memory at it. If your goal is to reduce the pauses, you're going in the wrong direction for most collectors. Okay, so not stop the world things. Concurrent marking is very commonly used now. CMS, G1, balance, C4, we all do it. Marking all the objects live is very simple in a stop the world situation, but if you have to do it while the application is still running, it presents some problems. Luckily, there's actually only one problem to be solved here, and I'll try and describe the problem. I call it the concurrent marking problem. You can paint it in 3 different ways, but it's basically one problem. We're going out there painting everything we can reach, and if nothing moved, we'll find all the live objects. However, the mutator might be taking a reference to an object I have not yet visited, putting it into an object I have visited behind me, behind my wavefront, and then getting rid of all the references to it. But if I didn't notice this, prevent it, track it, do something about it, and I just completed my nice live thing, and I said, okay, whatever is live is live, I will have missed the fact that that object is alive. And then I would recycle it, and I'll get something on top of it, and you probably won't be happy. So you have to somehow close that race. It's the only race, but it has to be closed. There are various techniques for doing this. Sorry, I got ahead of myself there. There are various techniques to do this. A common one is to track the mutations. So anytime you mutate, you write that reference, the connector says, well, okay, that I need to remember and get back to because I might have missed it the first time. There are various techniques for doing that. There are card marking techniques, there are buffering techniques, but most of them involve saying, if I mutate, remember that somehow, and come back to it. And a multipass marker for compared things will say, okay, I've marked everything, now go back and revisit all those things that were mutated. And if you do that concurrently, which you could, then while you're doing it, there might be more things that need to be visited, so you go back and do those. At some point, that set will be small enough that you will say, okay, now I'll stop everything and I'll just finish that, and hopefully it's small. In CMS, by the way, or at least to my understanding in CMS, there's no multiple passes, just one concurrent pass, and that does a remark. Anybody here hear about remark? That's what that is, okay? The issue to understand here is the work to do in remarking in a multipass thing is grows with the mutation rate. The faster your application runs, the faster you mutate the heap, the more work there'll be to do in a remark. It doesn't grow with the heap size, it doesn't grow with the life size, it grows with how fast you run. Okay? Important note. So you might be able to stay concurrent up to a certain speed and then boom. That's why you should test and see where it stops working. Incremental compaction, G1 and balance both use this, and I think my understanding is JRocket also used it in some collectors. I talk with more authority about things I can read the code of. So. This technique says I'll track some cross-region pointers between regions, say a megabyte or 2 megabytes in size in the heap, and then using that, I'll try to compact sets of regions that don't make me scan and compact the entire heap. So if I compact one region, I only have to scan for reference and into that region from other regions that point to it. And if I remember what that is, If I move one region somewhere else, I don't have to scan the whole heap. Maybe only 12 regions point to it, or 12 places point to it. So it tries to remember what points where. And when it finds sets that it has, where it's not the whole heap that points to the whole heap, but these 17 regions are pointing to from only 175 other places. And if I compact them, I don't need to scan 175 things, and it's less work, and it's an incremental, smaller cost than if I did a big pause. And then I'll come back and I'll do another set, and another set later. It's safe to let you run it down. So you identify regions that fit in a limited amount of time, hopefully, and then you compact and fix up the pointers. Now, the work for this, and it's important from a complexity point of view to understand that while there's a lot of good statistical filters and helpful things, and you look for the sparse parts and do all the those, generally speaking, as you grow the heap, the number of regions that point into any one region grows with that. Because in reality, the old generation piece is just the throwing of the dice. Everything just goes in there, and there's nothing really that keeps anything together. So things point to each other pretty randomly, and then a number of things that will point to one thing, the areas will grow. So the complexity of this could actually grow at n squared, as opposed to n. But it is effective in a certain range. Okay. I like to say that GC is mostly about delaying the inevitable, or has been for the last 15 years. Our approach at Azul was to actually try and break the cycle. And you can look at delaying the inevitable as adding more algorithms and more tuning parameters that let you push the problem forward. So generational collection is a very effective way of delaying the need to do big pauses. Not to get rid of them, but delaying them. And it actually finds a lot of efficiency in the process. And then when we say, well, I still have to collect the old generation, you can say, well, maybe I don't have to compact it as often. So maybe I can collect it concurrently and sweep it concurrently without having to stop the world or not for long. But eventually, you do have to compact it. So it's another delay. And then you can say, well, if I have to compact it, maybe I can compact it in pieces rather than as a monolithic thing. And you build an incremental collector for that. And that also has some nice alternative, right? But eventually there will be some amounting of popular places that you didn't want to collect, and you didn't want to collect, but they keep mounting up, and at some point you could get to a situation where you have to fall back to a full piece. All these are improvements, but they're all improvements of pushing a big thing forward into the future. So let's classify the collectors we have currently. I already said that these are the typical combinations. Looking at them in hotspot, ParallelGC is the most popular collector used anywhere in Java because it's the default collector. It's also a pretty good collector. It's monolithic, stop-the-world, copying UGent. Hopefully by now you know what every single one of these words means. Okay? I carefully tried to define them. It also has a monolithic, stop-the-world, mark sweep, compact all-gen. Both of these are parallel in current releases. But they're stop-the-world, they're not concurrent. Let's classify the CMS collector, the concurrent mark sweep GC. Now this is described as a mostly concurrent collector, both in academic terms and in all other terms. So given that it's called concurrent mark sweep, what do you think the classification of its new generation is? It is a monolithic, stop-the-world, copying agent collector. The CMS part only describes the all generation part of this collector and only part of the all generation part of this collector. It has a mostly concurrent non-compacting all generation. It uses a mostly concurrent marker, that is a trick we described, tracking mutations coming back to them. It has a concurrent sweeper, very good, but it doesn't compact. So how does that work? That's another part of the mostly. It falls back to its full GC when it has to compact. Remember when I said mostly is an important word? Look for the others. G1GC, which has been maturing, and you've heard a lot of good talks about it in JavaOne this time around. Let's classify that. Surprise, surprise, monolithic, stop-the-world, copying UGent. All hotspot collectors are monolithic, stop-the-world, copying UGent. It has a mostly concurrent all-gen marker, similar but not quite the same as CMS, and I won't get into the difference here. It has a stop-the-world, mostly incremental compacting alt generation. Again, all these words actually mean something, and I think they've been defined. So to key in, you have to understand that G1 was not designed to eliminate pauses. It was designed to avoid as much as possible doing a full GC. It's in the stated definition of why it was built. Okay? Now, when you see something say as much as possible, that means sometimes it will happen. That's what the fallback is to. Okay? In the incremental compacting alt-gen, it does what we talked about before. It keeps track of regions, finds regions that could be handled within a budget, stops the wall for the budget, does this thing, and moves on to the next and the next and the next. And this works fairly effectively at delaying and sometimes running for a week without the full G. But a higher load, a different structure might push you over. Okay, so we're running a little short on time because I'm too relaxed here. I'll go a little quicker. Application memory wall. This is why stop and won't actually really, really matters to the entire industry, not just because it's a node. Remember this thing? Now, let me give you guys a reality check on what a server is. But before I do that, how many of you program software that runs on servers? Okay. This is a server in 2013. 90% of you use less than 4% of a $4,000 server. You showed us that before, right? And that's the cheapest one on this list. These are prices off the Dell website today. And they're about to get even cheaper for ports when they come up with the new Intel stuff. So 128 gigabyte server can be had for about $4,000 or $5,000 right now. A 240 gigabyte server with 32 virtual cores could be rented right now on Amazon for $3.50 an hour. How much do you make an hour? So saving a gigabyte or trying to fit in 2 or 3 or 5 gigabytes is not motivated by cost of gigabyte. It's motivated by something else. And really, the application memory wall is an observation that application instances seem to have a hard time using this plentiful, cheap memory. The observation is the problem I did in this room. I didn't ask you what you do, but you seem to have a hard time finding a use for it or a use you're going to actually apply. The size of these application instances as a percent of server size is shrinking at Moore's law rates, and it's been doing that for a decade. If we look at this over time, we'll see some interesting observations, but a common thing I get from people at this point is, but come on, I mean, who needs 128 gigabytes, right? What does the application actually need? Well, this question has been asked and answered multiple times. This is a common example. You can make a lot of money. But, and it's just from, and there is actually no right number, right? The argument is not whether or not one of these numbers is right. It's what is right now. The actual right number moves at about 50 to 100x a decade, because that's how fast memory becomes cheaper. And Bill Gates actually said he never said that, so I'll give him. If you look at it as a history lesson, and I remember all these sizes, personally, and I tried something I call a tiny application size, which is the thing you would be embarrassed to tell people you broke into pieces. If I took a 1,000 entry array and wanted to sort it by putting it on a Hadoop cluster, I'd probably be embarrassed to tell people about that. But if I needed an exabyte sorted, that might be another way to do it. At a given point in time, that size shifts. So in 1980, it was already 100 kilobytes for tiny. And 1990, 10 megabytes was so small we didn't bother to break it apart, but a gigabyte was hard. In 2000, we had WebLogic running 1 gigabyte stuff on 2 to 4 gigabyte servers. And here we are today, or 3 years ago. Right now, the natural size for a tiny app should be about 100 gigabytes. So it's a very small fraction of a commodity computer. But clearly, that's not what you guys are using. There's been a flattening of that size around a decade ago. And that's the application memory wall. Now, what's causing this? It's pretty simple, garbage collection. Within garbage collection, what's causing it is the pauses, the practical time you're willing to stall your application without too much egg on your face. It's annoying to have a 2-second pause, but imagine a 2-minute pause. That's why you don't. And virtually all current JVMs will pause for seconds at a time at the current sizes that you guys stop, which is why you stop there. It's the root cause is really responsiveness to scale being limited. And that needs to be broken in order for us to actually get past this. Now, here are a lot of things it's not. This is not about efficiency. GC is extremely efficient if you let it pause. And it's not about speed, because the speed of your Java is pretty damn good. You can get good percentiles. It's just the occasional non-percentile thing. And it's not about minor GC events and tangents, because those you can get to be small. It's the really big pauses, the ones that you just can't explain to your boss or your customer or your wife. Because those are things you can't afford to have happen at all. They are equivalent to a crash. In fact, some of them are longer than a reboot of a server. So you would have rather crash than happen. That's what you need to get rid of. Now, here's one way to deal with monolithic stop-the-world problems. I borrowed this from Kirk Pepperdine. I use it in every one of my decks. This is a very effective way to deal with this. Okay? Let me teach you how to do this. You construct a benchmark, a Pascal benchmark, and you tune until you get this picture. And look how good that thing. And that's a 20-minute run, a 40-minute run. I mean, just ignore the fact that if you ran it long enough, you would have big bad things and that kind of behavior. And if you actually ran it for days, it would look like that. Okay. There are other ways to deal with this that we see a lot of. I call this creative language. It's renaming the problem to make it feel better. This is a really good example of that in practice, with an actual guarantee from a JVM. They will guarantee a worst case of 5 milliseconds 99% of the time. Marking hooks are amazing. I'll point out that 1% of an hour is 36 seconds. And if I'm in a low latency world, I'm allowed to stop the world for 36 milliseconds, 1,000 times a second. I've still met my guarantee. 1,000 times an hour. And these are other ways. Using the word mostly over the place is very creative. And then saying fairly consistent, typical pauses. Anytime you find these words, remember they mean the opposite of what it says. Typical will be this, and sometimes not. Fairly consistent, well, it's not quite consistent. Right? Okay, you can also do other things like measure what really happens to figure out what happens and actually try to do something about it. But this is, by the way, a picture of JHookup, which is a tool I open source, and you can download and use on any JVM, on any application as an agent. I'll give you this picture for your application. So what can we do to get past this? And I've got like 4 minutes. Wow. So we need to solve the right problems. And scale is artificially limited by responsiveness. That's the problem I'm talking about, because you guys are not using servers. You're using a toy part of a server right now, because, and you're using a lot of toy parts of them, because that tends to work. You'll take a server, put 20 things on it. You can't make one big thing work. But we need to unlink scale from responsiveness in all these metrics. And to do that, we actually have to eliminate all stop-the-world fallbacks, not push them further to the future. So everything has to go. Now, to do that, there are a few things that need to be improved. First is robust concurrent marking. We have concurrent marking, but it only works up to a certain speed. And then it starts falling behind and falls back to the full GC. That's called a concurrent mode failure. How many of you have seen that? Okay. Compaction is also something that needs to be at least not monolithic, stop the world, and hopefully robust. Concurrent compaction would be ideal. And then young generation actually has to be not monolithic, stop the world. If we want a 100 gigabyte heap, we better be ready for 3 gigabyte promotion. In a monolithic stop the world world, that's as big as the biggest pause you currently have. It has to be non-monolithic stop the world. Again, ideally concurrent. This is where we come in. Our C4 collector, classified using the same terms,